Okay, this is the section 2.2 on moment frame connection analysis and design. Um, for typical welded connections and bolted connections we saw yesterday, all of them are considered to be FR connections or rigid connections per code. Ours is a little special. It's considered a PR connection, and I'll go into that a little bit, what the two are. Because of the PR connection, there's more analysis and design requirements required for our connection. Typically, when you do a moment frame connection, when you model in SEP per se, people just do stick a line, a beam for a line for a beam, a line for a column. Where it comes to the connection, they just connect it and don't release any shear, any moment. So just making a moment connection, and that's all they have to do. So because that's considered rigid, the connection is not much rotation due to your bolt slip or whatever. But ours is different. We actually have to model how the connection performs for each connection. So if we use a lighter link or a heavier link, we have to capture that, and also I'll tell you how we model it later in this one. But we do have some procedure how to incorporate that in SAP, and I'll go into different ways of doing it later. But just to go over what a FR and PR connection first, and then followed by the typical analysis required. Why we are concerned with PR connections, sometimes doing analysis or design, and then connection modeling and some frame design. So typical PR connections here are from someone's paper. Basically, we're looking at a lot of these are single web angles, so you don't have any plates on the top and bottom. So double web on either side, and then even you have a T on the top and bottom. It's still, because the T is bending very easy, it's not stiff enough. So if you look at the curve, here's where they rank. So the single web, double web, and then they call this a top and bottom seat. So the stiffer it goes, the more moment it will take less rotation. So the less stiff it goes this way, the more stiff goes up. So theoretically, if there's no rotation at all, it will be going straight all up the line. And then the pin connection, what people do is there's no resisting, so it'll be on this line. So theoretically that's what it is, but typically it's somewhere in between. So you see all these different connections. So even for end plate is actually with stiffeners, and it's relatively stiff, so you're in the upper range. And there's a way of quantifying it as well. It's shown on the next page. So this is the classification according to AISC. We saw the same thing, M versus data. So this is a rotation, and this is the moment. So the difference between a simple PR and a FR connection is basically by the stiffness. So if you're 2 EI over L or less, then you consider a pin connection. If you're at 20 EI over L or more, then you consider a FR connection. Anywhere in between, it's what's called a PR connection. Okay, so that's how they define it. EI is the modulus from the column that you're looking at. Okay, and then the L is the height of the column. So I'll go to do some calculation for our testing and see where we fall later. So
the column and the beam.
this is actually the beam for just the beam. I'm sorry, just the beam of EI of the beam. L is the clear span. When we're looking at the base plate rotation, then is the column and then the height of the column. So all right, so that's how AISC classifies it. Also, this is for same thing, similar, but Eurocode has different classes on classification. So when you look at the moment, they classify rotation and moment. So there's a partial strength and there's a full strength. How they classify it also is basically if you could develop the moment of the the bending moment resisting of the connected beam. So like I said before, this is a kind of the ZXFY of the beam. If your connection it's stronger than that, then it's a full strength connection. If it's not, then it's a partial strength connection. So they have similar ductile, connection, semi-ductile, but just see how far you push the connection. If you don't reach a certain limit, they call it brittle connection. But the idea is you could classify it based on the moment strength or the stiffness of the connection. So there are two ways of looking at it, and they all come out with a little bit numbers that are quite different. So if you look at this, go back to classify it by, this is by the moment. AIS is just slightly a little less than asking you to develop the full moment. It says 90%. All you have to do is 90% to consider a full PR connection, and 20% down here. So it's very closely to this match the two. So what's the problem with PR connections, or typical PR connections per se? When you look at the curve, there is no elastic. I wouldn't say no. There's very little elastic portion. So it yields right away when you do typical PR connections. So if you have you have the two connections on either end. When you load it with gravity, you add this side, you subtract on this side. Okay, so the moment adds here, so it's going to yield on this side first. Yeah. Right. The positive plus positive, gravity plus earthquake. You add your positive minus, so your moment actually reduce on this end compared to this end. So when you go up, you unload it. Typically you unload straight line, and unload straight line, unload straight line. But each side is at a different point at that time. Depends on where you are. B prime, C prime. Okay. So this side, one side, is always higher moment than the other side because you're additive on this end. Okay, so when you do any kind of analysis, you'll see it is
the moment.
Moment is it's the same on either side when you're doing gravity. If you have uniform load, just bending, this moment is the same.
We apply
when you're applying earthquake so you have a positive on this side, a negative on this side, then your two positives is going to add. Then when you subtract, then you're going to have less moment on this side. However, earthquake also reverses, so you're going to be adding on this side and then subtracting on that side. So, but the first of them is going to yield during any push, or you're going to see one side is going to be higher than the other. Okay, so another concern is, okay, if I'm going to be using these PR connections, and since they yield so early on, what stiffness do I use for my drift check? Okay, for stiffness is when you have to put in, I have to use some kind of equation and get a stiffness to calculate your drift. Typically, drift or deflection is calculated with a elastic stiffness. So if you have the stiffness changes so much, which one do I use? Do I use the very first one that is yield, or some kind of secant stiffness, or tangent to the line where where your serviceability concerns? So that's it's hard to justify which one to use. Okay, so what's different from our connection? First is if you look at this one, our PR connection, I kind of did the same thing for those two, right? 29, 39, 37. Anything that's 20, or if you're looking at the stiffness, 20 or 90, somewhere in between is considered a PR.
Yeah.
So we are in between.
CA is
2EI over this one. I'm talking about C divided by A. This is percent of the beam. So this is EI. Ours is the
But the yellow highlight is 29% when you come up. What you call it?
Actually, I think you have the calculator. It should be A, not 1862. Whoa. Okay, I don't know how to use your calculator. Inverse?
Yeah, 29.
Yeah, it's actually not C. It's sorry, B divided by A. B is our tested.
Yeah.
Right. So that's
The stiffness of our connection. Yeah.
Depends on how stiff. If you look at this one, this is remember we tested 3 types.
Yeah.
The light, the medium, the heavy.
Yeah.
The light is very thin,
Yeah.
so that's why it's a lot more flexible. When you go to the heavy and the medium,
Yeah.
we're about 40%. You know, like no, 30 to 40%. Even compare the moment. This one is the moment. So this is the MP of the beam, CXFY. This is MY of the link, yielding of the link only. So if you take this one divided by that one, you get about 32% or 38%. So within the same ballpark as what looking at stiffness, looking at moment. So this is just to classify where we are in terms of the when it comes to either PR or FR connections. So since we are in the PR range, so this one is should be B divided by A. That's what we get.
Next question is why you divide the ME link to the MB? MB is come from the beam plastic moment of the beam.
Yes.
It's not the link.
No, the MY link. This is the moment of the link.
But the MP is the beam.
Yes, MP is the beam.
Why you define the link of the beam? It's not the.
One of the ways to classify it is to assuming you develop the full beam resistant connection. So you have your full string connection, your partial string connection. This is they're taking the beam baseline. You're using the beam moment as baseline, right? So if your connection could get more than the beam, then it's rigid. If you're less than the beam, it is not rigid. So our connection is the link. So we're saying if your connection is greater than the beam, then that's going to be a rigid connection. If we're always less than
the beam.
Yeah. Well, our link is only this much compared to the beam. Is that much. So we're going to be always less than what the beam. So we always will fall in that range as a PR connection. So next one is what you're trying to do is differentiate between the two. Is for traditional, what I call traditional is the ones before, is they typically yield under gravity load. Okay, just yielding under gravity load, your connection, their connection is yielding already. When we design ours, we're trying to design it with all the connections and have our link not yield yet, because we're gonna design. You'll see how it is. We're gonna do all the load combinations, and then earthquake plus dead plus live. We're gonna come up with a moment. A moment, that's the demand, and then we're gonna size the link for that demand. So which means we're gonna be in the elastic range. So we don't yield under those loads. We only yield under like a big earthquake. But remember, we're talking about all the designs in the U.S. are pretty much in the elastic range. So that's the same concept we're gonna take when we do a design later. But this is just a background of what we are. Some of the concerns between the PR connection and the FR fully restrained connection is this is directly from AIC 360. in the analysis of the structure, if you have a FR connection, fully restrained connection, the connection may be assumed to allow no relative rotation. But like I said, so there's nothing else you need to do. Just connect the beam and column and you call it good, and just design your connection. However, when you have a PR connection, in the analysis of the structure, the force deformation response characteristic of the connection shall be included. Okay, so how the connection deforms, you need to include it in your model. Whereas the other one, you don't have to include it. Okay, so now PR connections have sufficient strength, stiffness, and deformation capability. So strength and stiffness, the two we're gonna calculate. Deformation capacity, we tested it to see if you're okay or not. So we meet one of them already, the deformation capacity. But during design, we need to make sure it has enough strength. Obviously. Yes, the stiffness, it drift when you're checking. So, and I'll go into each of those later. So some more commentaries. Requires PR connections requires a separate analysis for serviceability and strength limit states. Yeah. Okay, what they mean here is serviceability is typically for your drift check, for your deflection check.
Deflection.
Okay, deflection and even drift, they consider that serviceability. For strength is okay. How much strength do I need? Like a moment, shear, and axial. Can my connection take that all the load from these cases? So you need to require separate analysis for the serviceability and the strength limit state. For serviceability, they say the analysis using linear springs with a KS, this is secant stiffness we saw earlier, is sufficient if the resistance demand of the connection is below the strength. So KS is, I'll go back to what KS means. The serviceability. This is the KS.
Yeah.
The reason why is in order to model this in there, you could do it because if you do it in elastic analysis, you could actually model the connection, the whole connection this way, and run it and do an elastic analysis to capture the true behavior. But typically, that's very, very time consuming for design. It's just you don't have enough time or enough computer power, and for one design it takes forever. So what engineers are trying to simplify it is they would put one rotational spring at each end, the one spring at each end of the connection. So when you have the beam and column, you do one each end, and that stiffness of the spring, that's what they're talking about is this stiffness, secant stiffness, and that secant stiffness they get it from somewhere serviceability and how much rotation in the connection. So I'll get into that later, actually looking into that a little bit more in our connection, but just to point out what people do when they have a PR connection, what's required by code right now. So you would need to, for analysis, use a linear spring with a stiffness at the joint. And also, a more careful procedure is needed that consider assume analysis consistent with those of the connection response. Well, we tested it. We try to model our connection with the backbone curve or whatever to make sure that we are we do meet. Our connection is consistent with the performance that we're modeling it. Okay, so how do people model these connections? Okay, not if they want to model the true behavior of connections. What do they do? First of all, obviously they have a test to see how the connection performs.
Yeah.
Okay, after they test, then they'll come out with some equation to approximate the how the curve goes. So this one is called a 3-parameter model, 3-power model. So that's the n equals 1. This curve goes like this. If you increase the n, this curve goes up like that. If you keep increasing the n, it becomes an elastic plastic model. Okay, so the n drives how this goes up. So people approximate it with this equation. So imagine, since there's a lot of analysis and a lot of different connections, the n is going to be different for each connection. So it's kind of hard to say what that would be. So if I apply this equation to our test, okay, that's our heavy test. That's what we get for n1, 1.52, and 3.5. You can see it
The
goes.
n is
N is the power. So n is just some number that you come out with to fit your connection.
yeah.
Okay, so you do the analysis, you come in here, and okay, which n fits my connection better?
Yeah.
Okay, so that's one way to model the connection. Another way is also very similar, is called the tangent stiffness one. This one, as well as, instead of n, they call it a shape factor to account for the decay rate. Very similar concept. It just, instead of calling it n, they call it a c. And the equation is slightly different, but the same concept is you get a different c,
Yeah.
you get a different equation. I mean, different shape.
Yeah.
Okay, so these are the different tests they propose. That's what they propose. This is a different test. That's what they propose. If you see, this one is a 0.5. This one is 0.34. This one 0.525. This one 0.22. It's all over the place. So it's very specific. And what that means is, for each beam and each column and each connection, you would have the specific C.
Yeah.
Right. So what people have is actually they have a whole bunch of data in the database. If they use it, they could go look it up and use these C values and approximate their connection. So there is something in there. A lot of people do for wind design per se, like in the East Coast, when they use those bottom seats, if they want to analyze it, they do have a database for them to go to. Okay, I have this beam, or I have this angle that matches what was tested before, so my C value is 0.505%. So then when they go and do the model, then they model it with that in mind. So that's how they capture the actual behavior of the frame, because of the PR connection. You can see these are yielding very, very early. You blow it out, it's kind of starting to yield. Okay, so again, this is what we saw before. Nonlinear moment rotation is needed to consider analysis and design for VR connections. What stiffness do you use for drift check? What load sequencing should be used for the analysis? What is the actual response and strength of the PR connection and how it affects the stability of the columns? So what we do calculation right now, the K, when you're doing K for the column, you assume that the beam is restraining it. So if that's assuming a rigid connection, so all the equations that derive in those K calculations are assuming the beam is rigid enough to restrain the column. What if now you have a PR connection? You're not stiff enough to restrain it. What happens? So you have to kind of look into modifying the K to do your column design. Okay, so boil down to the 3S, connection design concerns. Strength. How is the PR connection influence the force distribution to the beam and the column? What strength should the members have to resign these loads? Stiffness. What connection stiffness do you use for drift check? And the stability. Stability is related to what is your effective link to use during design for your beam and columns. So let's see how we address some of these in our connection. So our connection model, instead of a what they call the I would say connection fitting the test results, and each one have a different C value. We try to look at the contribution of each component differently and sum it together to come up with a model. And we also obviously have to compare to see how good compared to the test result. So what this does is, instead of having a different C, you go do the different equations to come out with each component. That's your stiffness. So this equation should apply to all our connections, light, medium, heavy, whatever we use, because the contribution of each component is considered here. So we model it as 3 springs. So K1, I think I flipped it somewhere else. K1, K2, K3, K1, K2, K3. Your flange contribution, bending of the flange, is K1. So you can see W times t, t cubed divided by 12 is g divided by the g. This is the bending of this flange. When you pull on it, this flange tends to bend. Okay, that's the first term. The second term and the third term are axial. This is the non-yielding region. So these regions here, these whatever regions here, and this one is the yielding region, the contribution of this yielding region. So K is, it's just EA over L, right? EA over L is your K. So if you look at this one, L is the length of the yield link. Okay, A is just the thickness times your width. This is the width, this is the thickness. E, that's just E. So if you look at this one, this is EA over L. This one is a little bit more complicated if you go, but still you will see the E, A over L. So here's the E, here's the A, here is the L. L is one column side, you have to consider this column side, plus this C, plus whatever is, if you go into here, if you have more than 4, then you consider it. If you don't, then you don't consider it. So these L is covering that. Again, E, A over L, it's the same thing. This one, flange bending, if you look at it, is the 0.75 is for some kind of adjustment factor, because the column flange also bends a little bit.
Yeah.
Right? When you bolt it up, when you pull on it, the column flange would bend a little bit, and that's just approximately, I would say, fudge factor to adjustment factor to account for the column connection. So, knowing the geometry of a connection, you could calculate K1, K2, and K3, and then you just assume they're in springs in series, and you calculate the whole effective stiffness for the connection. Right. So, knowing just the geometry, you don't need anything else. Just knowing the geometry, we could figure out a effective stiffness for the connection. So no fitting of the C or the N is required if you do it this way. It's this component model it's been used in the EC code for a lot of their connections. So if you're familiar with that, that's what they adopt for that.
We use the KEF for modeling.
Yes, we use the KEF for modeling, and I'll show you. And the KEF is on the springs.
Yeah.
So, and I'll show you when we get into SEP where do we put this KEF factor. Okay, so once you know these ones, then you have the parameter, the KEF. If you want to do the moment rotation, so there's many ways of people modeling it. Modeling KEF is only for the axial spring stiffness. Okay, so now how do you convert it to a moment? So there's two models. I'll show you a little bit later here. This is a nonlinear axial spring model. This is a rotational spring model. So for your axial, everything's related to delta, Py, P link. For the moment, the spring is related to the data y, My, and MPR. And how you relate them is, well, the P is calculation just the AY of the link times the RY times the FY. The APR is this equation that I showed before. Maybe you haven't seen it. AY times RT times FU. And then M is just the PY, the link, times the lever arm. The DB plus this. So the DB is the beam of the depth. Beam depth, that's the axial force. When you're doing it, is the force times distance. That's your arm. So that's the MY. And you just substitute the PY when you want to do the MPR. So that's where the MY and PY come from. And that's where the PY and PR. And delta Y is a term that you just take your PY divided by the KEFF. And then you get the delta Y. Data Y is data Y divided by, this is half the beam rotation. So we're looking at the beam center line. And that's where data Y is coming from. Okay, we'll go into this one a little bit more and actually model it. When we model in SEP, we'll go through these equations, and also all these has been in the Excel spreadsheet, so you could go and model some things and see the different changes. Okay, so after the your knowing the geometry of your link,
Yeah.
you go in here and you choose either method to do your analysis. So ours right now, we're taking this one to do the axial link.
Yeah.
Okay, so heavy test comparison. This is our model. This is the different end comparison. Okay, so this is our 3 from this here. Okay, that's the comparison with the different n value. That's, as you can see. Here is the actual test. Okay, here again you plug in those three power with the n, and then by the component method. So we match very well. Okay, so we match very well for the heavy test. That's why we know we're
The
using.
heavy in the line, the medium.
Yeah.
So we name it.
Yeah, that's how we named it for the testing before. But right now
But
we're not offering
how
we're not
we
offering
know
the media previously testing was the light, the medium, and the heavy, and how we come out with that was just
Yeah.
based on the thickness. Remember 0.25, 0.375, and 0.5.
Yeah.
Because of the buckling of the lighter ones, we're just restricting everything to the half an inch because we didn't see any buckling.
So right now, T-link is the half.
T-link is only half an inch.
Yeah.
Yep. Until until
Heavy.
further testing.
Yeah.
Heavy, but remember we could neck this down
Yeah.
to whatever we want.
Yeah.
So for our catalog, we use the same heavy, medium, and light.
Yeah.
But instead of changing the thickness,
Yeah.
we're changing this area,
Yeah.
the width. Okay, so the PY is basically area. So how do you get the area? Either increase the thickness,
Yeah.
or decrease the thickness, or
Or
increase the
the
width, or
width.
decrease the width.
Yeah.
So yeah, so we're adjusting this
Yeah.
instead of adjusting this for now. Okay, so design beam for gravity low is simply supported. So analysis and design procedure. Here's what we're trying to do. Actually, for the beam, we wanted to carry the gravity low, assuming it's a pin-pin connection.
Yeah.
One reason for that is
Deflection.
deflection. We want a stiffer connection first to start out, but also for retrofits. When let's say if you want to remove the link
Yeah.
and on the cotton bottom, you have to shore it up. For us,
Yeah.
if it's actually taking out the gravity load, so you can take out a link cotton bottom and leave it whatever it is without having shore. Then just add the link to the cotton bottom, and you're good to go, because you designed your beam for the gravity load for the simple beam for all of it already. So when we go to the SAP and the Excel sheet, I'll tell you what step that is and how we're doing it. But the first thing is we are designing the beam for gravity load. Not lateral, just the gravity load for assuming is pin, assuming there's no moment from the contribution. Okay. The second step is we'll use linear rotational springs and linear axial springs for the drift check. Okay. So that's how the K we're saying is, that's what we're using for drift check. So that's where the stiffness. The strength and stability, we'll use the effective link or the AISC Chapter C direct analysis for stability. I'll go over these a little bit more when we go into the Chapter C on AISC 360 on the design, what these different methods mean and what they're trying to capture. And then design connections for the probable link axial capacity. So what is looking like is, here is our typical your analysis for traditional PR connections. Okay, I kind of simplified it. What they have to do here is, okay, their stiffness, it comes into here, and use this stiffness for their design. Okay, for us, we are designing our link to be less than this U, where U moment. We are always keeping the gravity and lateral moment below the U. So here's the yield. We actually applied 0.9 to it, so it's going to be always less than the yield. Alright. So yield of the link is just ASFY times 0. ASFY. That's
ASFY.
Yeah. Times the depth is your yield moment.
Yeah.
Right. That's what we always trying to keep it below this one.
Yeah.
So that is actually a lot of cases actually our limit, because we're not strong enough at this time, because we only have 3.5 inches times 0.5 inches. So when you look at the strength, that's a lot of times that would come into govern as well. So
we design the yield is elastic.
Yep. We're designing it to be elastic. We have to do it for this one, and the good thing is, if you're designing it to be elastic for your drift check, then you could use this initial stiffness. Then you don't have to worry about which stiffness do I use for drift check.
Yeah.
We're just using our elastic stiffness. Okay, how to keep the link below your low yield? Basically, we're gonna do all the building low combinations. You select your members, the beams and columns, and I'll go to this one a little bit later, but basically we're saying we're going to use the seismic low combinations to do the design of the link when we get to that point. And then P delta, small delta, big delta, I'll cover that a little bit more. So essentially, once you have a moment, you check it for less than PY link. And we even put it with a safety factor in there. These are some of the analysis with showing you what happens when you apply a lot of gravity load. This is a lot of gravity load. So with no gravity load, your frame performance goes like that. A little bit gravity load, a lot of gravity load, your frame capacity is a lot less. Yeah. So if you think about this is your base shear. This is your what this response is essentially saying. I'm pushing that low with a certain low, and I'm keeping track of that frame displacement. Yeah. Okay, so this is the low, and this is the frame displacement. Yeah. Okay, so when you push over without any gravity low, you get the top curve. Okay, with the maximum, whatever gravity low, not even maximum, you get the curve, and also you get a little P delta. That's where the P delta comes in. This is the P delta, because you're adding a lot of gravity load. It's tipped. It's starting to tip over, so you can see the difference. Okay, so we did a lot of study on making sure that it is elastic. Make sure the design is elastic, and we don't go into the elastic region. So that's all the analysis checked before. So you can see this P delta is very significant when you get to a lot of 20 kips per linear foot. Per foot. I mean that's. Yeah. That's like 15,000 pounds per foot. That's a lot. Yeah. So that's why these are just analysis. So summary of the SAP analysis were this. I had to do this to prove that the procedure that we're proposing is okay, and I've gone through a lot of different analysis, make sure it could work. So design frame to behave elastic for all cases. Okay, a frame is elastic. You can predict the ultimate load by hand calculation, especially for one bay, one story. This number we can always calculate by hand, and it's just related to the MP of the beam and then the geometry. So that's very easy to do it. So we know the upper limit on the frame capacity. So the design procedure, like I said, the C sub D is where we actually do the delta M. Now I'll cover what the C sub D later, what we use it for. Actually, this delta M is where we compare to the code allowable, not the delta S, is the delta M. And that's what the C sub D is doing, is actually trying to take your elastic, multiply by a certain factor, and that's what they think your frame is going to be at the ultimate deflection. So we're always trying to below yield. And when we check delta, delta M for the code, we use whatever C sub D that's associated with the R. So if we're using an 8, then we're using a C sub D
of 5.5. That means the deflection is going to be more than the C sub D of 4.4 or 4. So design beam, just to summarize it, simply calculate delta with linear springs, design beam and column for all the co-combinations, check the link yielding, and then we will calculate VPR if we have to, and then we check the beam column based on this one. So recheck beam and column is important because when we start on the first round, our procedure is assuming it to be fixed. Okay, for other engineers to design, what we are going to do is we're going to skip that step because we know our link geometry. We're going to actually jump to a certain step, but we still have to iterate through it a little bit for the design. So I'll go through the different steps with you. Actually, that will be next when we talk about what we need to do to design our connection. And there's 18 or 19 steps that they have to follow. Engineer have to follow, or we have to follow when we're doing the design. So differences in models. Here's what the axial model look like. We actually have axial links on the top and bottom for the model. For the rotational spring, you just put the rotational spring in here. This one is a lot simpler to do, what engineers will choose, but we started doing this one, so we're going to stick with this, and we actually modify this one a little bit. These are no longer here, so this goes all the way to the end, and I'll show you how we're doing it and how we get those numbers from the beam and column. So the close up for this one is actually that's just the rotation. So SAP has got all these elements for you to model it. Again, these, don't worry about it. I'm just comparing the different comparisons for. This is essentially to show the rotational spring versus the axial spring. So you get pretty much the same behavior. It doesn't matter how you model, which model you pick. Your behavior is pretty much the same. And this one is, let me see. So there's 4 of them here. NL, this axial spring, rotational spring is in SAP. So you can see these 2 here. This one is our own. I rolled it in Excel, so this one we could do the approximation as well if we need to. And this one is what we're doing in the software. We're only doing our elastic in the software in the strong frame selector software. We're only doing the elastic. So what we're trying to see is make sure we match the stiffness, obviously, it doesn't matter which method you use, because since we're doing an elastic design, all we care about is in this range. So if you look at the different ones, we're very good in terms of how we compare with the other ones. Okay, so review. SST connections do not yield under gravity and lateral, and that's what we're trying to do. Frame behaves elastically.
Include the wind load and this.
Lateral or wind load. So typically when say lateral, it's typically either wind or seismic. So, and when you look at a load combination, I'll go over that later. You don't combine wind and seismic. You only do just one or the other. So frame behaves elastically to design drift requirements or link force. Model with elastic or the other one with the hinge for drift check. Link yielding force is calculated based on moment demand or from the spring. You can actually read it off the spring in SAP. That's one good thing is instead of having to calculate a moment divided by the depth in SAP, you could just read off what the spring axial forces are. So there's different models how to do that. Beam column force is calculated for VPR reasonably well. I'll go into the pushover analysis a little bit why we do that if we want to do that. Some for design it's not required. For a lot of retrofits here in the Bay Area, Southern California, there's a new FEMA 807 code that you actually tell them how your frame is actually behaving. So if they require that, then we have to do the pushover analysis to tell them what the frame is behaving. Instead of just giving the elastic portion, they want to know how it behaves until it's it breaks until it's 5%. So that's it for this one. I know you guys have questions, but you know, anything at this point. It's a lot to chew on, especially this one. When I talked to our engineers the first time, you know, they have to think about what we're trying to do, because it's a innovative connection. Because it's a PR connection, there's a lot more involved for the analysis and design as well. So it's not as simple as what you would see the other ones.
Like the ways we come up with the PR, we try to get the stiffness to model.
No, it's just because yesterday I gone over the ways. Why do we want to go, you know, get some of the benefits when you